is test number 3. You see, question 1 is we give you a couple of functions like your quiz, and we want you to find the Laplace transform, okay? So this is going to be the first one. The first one is find the Laplace transform. Find the Laplace transform of each function. Laplace transform of each function. Okay, to do this problem, you need the following theorems. Okay, I'll list the theorem for you. Then you know what we expect you to do. Okay, this is it. The first one is we are interested in Laplace of the unit step function. Remember, UCT. You know that it's going to be e to the negative CS over S. That's first one that you need. 2 translation theorem. One of them is Laplace of, you see UCT. Remember, if you change the T into the T minus C, have T minus C. So the result will be what? The result will be e to the negative CS. E to the negative CS F, okay, Fs. Okay, so as soon as we see that UCT, we're going to get is e to the negative CS, is not e to the negative CS divided by S. Okay, that's the third one. And the second one, the third one, if you do the translation for the S, remember, Laplace of e to the AT, F of T is going to be equal to the F of S minus A. That's when we get those non-factorable terms. So it's like you write the Laplace of the function, but you change the S into the S minus A. And the fourth one is when you are going to use the derivative. Okay, the Laplace of, if you have a function like a power of t to the n f of t. Okay, if you want to find the Laplace transform of this type of function, it would be very easy. You find the Laplace of f of t and yet you differentiate it. It's going to be -1 to the n, remember? Then the nth derivative of your Laplace transform. Okay, so if it's going to be t f of t, it's going to be just simply negative f prime of s. If it's a t squared, it's going to be what? It's going to be f double prime of s. So if you see this function, the rest are going to be just, you know, f of t is going to be sine t, cosine t, e to the t. Okay, those numbers that we have. So in this question, we give you a couple of these and we ask you to find it. Yes.
For the fourth one, are you going to have any where we're given the Laplace transform and have to find the inverse for the derivative one?
Yeah, all of them are the same. Yeah, this is the Laplace. So the second part is going to be good. That's question number 1. We find the Laplace. Question number 2, we get the inverse. Yes.
Okay. Curious, like how would we be able to tell that it's a derivative function for that one?
To get this one?
Yeah, like if we're given f of the f of s, how would we get it back to the t to the n power? Because wouldn't we just like assume that you just have to do the opposite?
This mostly the direct one is more popular than the other one. You know, you get the other part is, you know, is not going to be used. It's going to be used in some other format, and not this one. Okay, but it's possible. It's possible. Okay, but you know that to finding the Laplace of t n to the f of t by definition is difficult. It need a number of the integration by parts. So that's why we know we record it, then we go for it. Okay, and you will see I'm going to use all of them in a minute. Okay. So we check, this is it. We give a couple of these function and then we ask for it. We did some of them before, but I'm going to do it again. So this is the one that we're going to do. Number 1 is Laplace transform. Exactly, you have to use these. Okay, so we go for it. This is it. Part 1. Part 1, the function is f of t equal to e to the negative 2t, okay, cosine of the 4t. That's it. So in this case, as you can see, because of this coefficient that we have, so we have to use the translation theorem, okay, this one. So what we do is we find the Laplace of the cosine of the 4t first, okay? So solution. So we find the Laplace of cosine of the 4t, which is easy to find. Okay, what's this one? Remember, Laplace s over s squared plus 16. Okay, this is the one. This is your f of s, if you like. This is going to be your f of s. Now you have the coefficient of the e over here, okay? So the Laplace of e to the negative 2t cosine of the 4t, okay, is going to be equal to what? It's going to be equal to the f of s minus, okay, a is a negative 2. So it's going to be s plus 2. Then you substitute, and then you're done. Okay, this is it. So it's going to be s plus 2 on the top, and on the bottom, s plus 2, all square plus 16, and you're done. You don't usually simplify this one, just show that this is related to the formula that comes. Okay? Any question? You can do this one directly, but you need integration by parts to be able to do it. Okay, you see the e, just compare with the formula, you realize you have to use the third one. So you have to find the Laplace of the function, then change the s into the s minus a. A is a negative 2, so that gives s plus 2, and then you're done. It's very popular for the inverse function. Okay, that's the first one. Any question? Part two is straightforward. You get a couple of u function.
That's what we can't do.
So this is going to be the k, okay, for the part 2. Yes, this one. This is it. So for the part 2, your f of t is equal to the t cubed. Okay, it's going to be t cubed plus 2 u2t, and that's minus 5 u40. Okay, easy function. Okay, just a unit step function. You go for it. So the Laplace transform. Laplace of f of t is going to be Laplace of the first one. Okay, I rewrite it. Is the Laplace of the t cube minus 2 Laplace of the u2t minus 5 Laplace of u40. So it's all unit step function, and we just substitute. Yes.
Is it originally plus or minus
Which one?
for 2u2t?
It is a plus. Okay, that's plus. Thank you. Okay, so let's go for it. What's the Laplace of t cubed? Is going to be 3 factorial, okay, which is going to be 6 over s to the 4. Remember, n factorial, s to the n plus 1. Plus 2, you have u2, so that give you, this is it. Remember, e to the negative 2s over s, and you have minus 5, and we have a u4. u4 would be e to the negative 4s, 4s over s. Okay, just a simplification would be just Laplace of f of t. Any operation like 3 factorial would be 6 over s4. Okay, and that will give you 2 e to the negative 2s over s minus 5 e to the negative 4s over s, and be done. You don't need to find those common denominators yet. So that's a couple of u functions, just to remind you that you have to know that. Okay, any questions? Part C is with a t. Part C, the function is f of t equal to the t squared. Okay, t squared sine of the 2t. We have the power of the t, so you have to use the derivative this time. Okay, you have to use this formula, t to the n f of t. So remind ourselves that the formula that we are going to use for the solution. So we know that the Laplace of, okay, t squared, whatever function, not this f of t, I'm going to call it g of t. Okay, this is going to be -1 squared times the Laplace, the derivative of this Laplace of this function. So it's going to be second derivative. I call it g of s, just to remind you. Which one? No, it's the second derivative. Double prime, if you like. Okay, double prime. So the -1 squared g double prime of this. So what you have to do, you have to find the Laplace transform of sine of 2t first, then take the second derivative in this case. Okay, so Laplace of sine of the 2t, okay, is equal to what? Sine 2 over s squared plus 4. So this is going to be your GS, if you like. Now you have to differentiate twice and just move it up and get the result. Okay, Laplace transform of the function. Now the second derivative, just to go back, substitute with that. So differentiate using the quotient rule. So g prime of s is going to be equal to the derivative of the top, bottom 0, bottom top is going to be negative. Derivative of the bottom is 2s times 2 would be 4s. Okay, divided by the bottom square, s squared plus 4, all squared. That's g prime. We want to find the g double prime, so we better move it up and differentiate it. Okay, so it's going to be equal to -4s, and that would be s squared plus 4 to the -2. So apply the product rule to find the g double prime. Okay, so it's going to be g double prime of s is equal to the derivative of the first times second would be -4 times the second one, s squared plus 4 is going to be -2. Okay, the derivative of the second first, you have to use the chain rule. So we bring the -2 down times the first, so it's going to be plus 8s, s squared plus 4, 1 down, -3, then multiply by u prime, derivative inside, which is going to be 2s. Okay, derivative of the first time second, -4, second first, it's a -2, s squared plus 4 to the -3 times 2s. So you just, you can change these powers into the positive, and then you're done. Because -1 squared is just positive 1. Okay, so there you are. So g double prime of this is going to be -4 over s squared plus 4 all squared. Okay, 2s times 8s would be 16s squared over s squared plus 4 all cubed. So this would be the Laplace transform of t squared sine of t. Okay, because you know the formula was -1 squared g double prime of s. Okay, so this is simply equal to Laplace of the t squared sine of 2t. So if you get higher power of the t, it takes more time. Yes.
Is there a specific reason why you didn't keep the product rule for the first one? For g prime?
Product rule?
Yeah. Like,
Why should you do?
You could have taken the two down and then had x squared for the second one.
You can do that one in that. But the quotient rule is easier. Yeah, it doesn't matter. You can, but the quotient rule for that one is easy. Okay, any question? So as soon as you see that power of the t, you must know that you have to use the derivative to take it. Otherwise, the other possibility is just direct formula. You need twice, you have to use the integration by parts to be able to take care of it. Okay, so that's going to be the first one. Any question? So we give you one with the lower power, but we are going to test it because that's important. Yes.
Problem number. Pick up that number.
Okay, so this is it. All of them can be done directly, but it takes time.
Okay.
If you want to do it, in the equation. So let's have one more. Part D, the power is lower, but the function is different. So the function in question is f of t equal to the t cosine. Okay, since the power of the t is 1, so you just need the first derivative. Okay, so this is the formula that we are going to use this time. I just remind you the Laplace of t. Let's say gt. In this case, it's going to be just negative g prime. Because it's a negative 1 to the end, okay, and it's 1, so you just differentiate it once. So you are going to find the Laplace of, the Laplace of cosine of t, which is going to be s over s squared plus 1. Okay, that's going to be your gs. You differentiate it and do that. Quotient rule again for this one, g of s equal to, when the power is 1, use the quotient rule for the denominator, s squared plus. Lift of the top bottom would be just s squared plus 1 minus lift of the bottom times top, negative 2s times s divided by s squared plus 1 all squared. So we continue on the top. It's going to be s squared plus 1 minus 2s squared. And this is s squared plus 1 all squared. Okay, combine the like terms on the top. So that give you what? It's going to be 1 minus s squared. 1 minus s squared, and this is going to be s squared plus 1 all squared. Okay, so that's going to be g prime of the sectors. So just a negative sign, give you the result. So the Laplace of the t cosine of t is going to be equal to, the negative 1 minus s squared divided by s squared plus 1 all squared. We can apply the negative sign to the top, write it down as s squared minus 1 over s squared plus 1 all squared. Done. Okay, so when it's a power is 1, we just need the derivative, the first derivative. When it's a square, you need the second. Of course, it's going to be lower power because it takes time to be able to. But there are nice applications. I'll show you one of them of this formula that we are interested in. Okay, there are some difficult integral in calculus 1, and you never be able to find it. But with the notion of the Laplace transform, you do it in a couple of seconds. And you need this formula to be able to do it. Okay, so that's a part D. Part E, we did it before, it's just a unit step function. Remember t squared, t minus 2 squared, you bring it up. And the part F, we did both of them before. Just check the practice quiz that we have. Okay, I just, I can write the part that we create that function, but we did it. Okay, so this is the function 0 t less than 2, and this is t minus 2. In fact, that was one of the questions on your quiz. Remember how we're going to change this one into the unit step function? You remember? Okay, so it's going to be h of t equal to, it's going to be h of 2 equal to the what? We are going to break it or pull it out. So that gives you t minus 2 all squared. And the leftover is going to be 0, 1. Okay, so this is it. So the function in question is going to be, this is the u function. So you have u2t, t minus 2 all squared. And that's exactly the correct version of the formula that we have. Remember f of t minus c So the Laplace transform of h of t is going to be equal to, because of the u, you have the e to the negative 2s. Now the Laplace of this is t minus c. You want to find the t. If you add the 2 here or drop the negative 2. So it's a t squared. So it's going to be times the Laplace of t squared. Okay, and the Laplace of t squared is what? T squared, and is equal to 2. So that gives 2 factorial, which is the same as the 2. And on the bottom, we get S3. So the final answer is 2e to the negative 2s over s cubed. Okay, so I just use the first translation theorem to it. Yes.
When you get the locus of t squared, because it's t minus 2 plus t squared.
That's it, yeah. Plus, yeah. So this is going to be number B. Okay. And let's do the F so we complete everything that we have. Another function, h of t equal to, we're going to have them when we get to the differential equation in a minute. So the function is cosine t, t is less than 1. And the second part is t minus 1 plus cosine t when the t is greater than or equal to 1. Okay. Any suggestion? Remember how we're going to change this one? We get the cosine t out first. Okay, solution. So h of t would be the cosine of t. Okay, cosine of t plus. Okay, plus that gives you 0, 1, 0 and t minus 1. And then we pull out the t minus 1. So that gives you cosine of t. You pull out the t minus 1, and the leftover would be u1t. Okay, so your function is going to be cosine of t plus u1t t minus 1. Now find the Laplace transform. So the Laplace of h of t would be the Laplace of cosine, which is s over s squared plus 1. And because of the u1, you have e to the negative s times the Laplace of t. Because that's a t minus 1, t minus c, we change it to the t. The add one. Okay, so the final answer is s over s squared plus 1. And the top would be e to the negative s. You know that the Laplace of t is going to be 1 over s squared. So that is going to be the case. Okay, so that's the Laplace of h of t. And be done.
Why is it over s squared? Oh, yeah.
N is equal to 1, and s to the n plus 1. Okay, so this type of Laplace transform we are going to be interested in. Okay, that they apply in these 3 theorem that we have. So just give you a couple of them. Just make sure the theorems are ready, use and just apply it. Okay, that's case 1. Any question? Case 2, of course, the other way around. Laplace inverse. We are going to use Laplace inverse quite a lot in all the other problems. But let's check to see what you are going to have. 2 different types. Any questions? So going to the, are you done? So the second question. The second one, finding the Laplace inverse of this type of function. There are a couple of cases, and we are have it over here. We are not going to give you anything complicated in this part because you're going to see much more when we get to the differential equation. So find the inverse. Okay, find the inverse. The inverse Laplace transform. Laplace transform. So, we did the case 1, we did it. We can quickly repeat it. So the first function is this one, f of s equal to 2s minus 3 and s squared plus 4. You know that we rewrite it, we break it. One with the S on the top cosine, one with the constant on the top side, and then we're done. Okay, so the solution is going to be Fs is going to be equal to the 2s. This is s squared plus 4 and minus 3 s squared plus 4. So the Laplace inverse is going to be equal to, the first one is the type of the cosine, s over s squared plus 4. So that gives you 2 cosine of the 2t. For the second one is a constant. You are going to do it by the sine. That's s squared plus 4. You need a 2 on the top. So we divide the outside by 2. Okay, that's it. So the leftover is going to be simply sine of the 2t. Okay, we know it. We write it down right away. So for the sine, make sure that you create that situation. Okay, that's the first one. That's a type 1, straightforward one. Type 2 and 3, of course, you need the translation. So the type 2. The type 2 is Fs is equal to, is equal to the e to the negative 3s divided by s squared plus s minus 2. As soon as we get e to the negative 3s, there is going to be a translation. Okay, so you have to find the f of s first, then change it to the f of s minus a. A is a negative 3. So change it to the s into the s plus 3. So you have to work on the leftover here to be able to do it. So you have to find, you have to find the Laplace inverse of this function first. Then you translate, you shift the s into the s plus 2. Yes. Yes, it is always positive. No, I said when you translate it, when you translate, translate it to the f minus, yes, it's positive, yeah. Okay. So this is going to be the case. You check the denominator, because if you remember that formula is e to the cs. I think that's what the formula that we have. Okay. So then we switch it. Okay, so you have to do the inside one first. Okay. So you do the inside one first. It's easy because it's factorable. So it's going to be 1 over s squared plus s minus 2. Okay. And so it's factorable. So that give you what? S plus 2 times s minus 1. You break it into s plus 2 and, minus, if you like, s minus 1. So we check it. If it's going to be okay, we are done. Otherwise, we are going to create it. Okay. So that's going to be 1 times s minus 1 would be s minus 1. And this would be negative s minus 3. So the result would be negative 3. So we divide both sides by negative 3. So negative 1/3. And this is going to be negative 1/3. Okay. And so this is going to be negative 1/3 s plus 2. And this is going to be minus plus 1/3 s minus 1. Okay, find the Laplace transform of this. So it's the Laplace inverse of 1 over s squared plus s minus 2. This is going to be negative 1/3 e to the negative 2t, the first one, plus the second one would be 1/3 e to the t. So this is going to be, that's your f of t, if you like. So this is going to be your f of t. And then you change the t into the t minus c. So the Laplace inverse of the given function, this is it. Laplace inverse of f of s is going to be equal to Okay. So you just have this is it. That's going to be the one. So I have this one, and then I have the e to the negative 3s. So that would give me e to the, what is that? You need a u function for this one, yes? That is going to be, I just get confused, this is one. So because of the e to the negative 3s that we have over here, okay? So it is going to be u3t, okay? So it's going to be u3t, then times 1/3 of the, okay? Let me just check that one. I get confused with this times. T minus 3, yeah, that's f of t. So u3t, f of t minus 3. We accept it, you know, if you write down it in this form. You don't have to go back and substitute it. You get this, okay? So because of the e to the negative 3s that we have, so it's going to be a translation for the t. So we find the function, okay, your function, you call the function f of t, then you change the t into the t minus c. Okay, so this is a theorem that we talk about. Look at this one. This is the second theorem that we talk about it. This is the one. You have e to the negative cs fs. So I find the fs over here. Then I need the uct f of t minus c. So because of the c over here, I'm getting the uct, but I have to change the function into the, from the t into the t minus c. Okay, so we accept it if you write down as f of t minus c. You don't have to rewrite it again. Okay, so that's a case 2. Any question? Now we need one more. Yes. You see, at the beginning, as soon as you see this factor, e to the negative cs, you recognize this must be done by the translation. That's the key. So what you do is you take care of the leftover first. You take care of the leftover to be able to find your f of t. Okay, and as soon as you find f of t, because of that translation, so you end up with the u3t f t minus 3. Okay, so that's a good indication. That now this is case 1 of this group. The case 2 is going to be this one. It may come with a factor for this. Look at this one. You see what's the difference between these two. So f of s is equal to the 1 over s squared minus 4s plus 5. Okay, what's special about this one? It's quadratic, but the denominator is not factorable. Since it's not factorable, you have to use the completing the square method, and then you have to use the other translation. Okay, so this is going to be the case. Solution. So what we do is we are going to do the completed square first. 1. Remember, we divide the coefficient of s by 2. So that gives us s minus, s minus 2 all square minus always b. Because when you square it, that gives s square twice of the first time, second for s, and there's going to be a positive 4. We don't have the positive 4, so we subtract it. Always 2 square, which is 4, and then plus 5. Okay. Now the result is going to be what? Is going to be 1 over, 1 over s minus 2 all squared plus 5 here. So, plus 1. Okay, now s minus 2, you can call it s, so that would be 1 over s squared plus 1, which is the sign. Okay, it's going to be the sign, but since you translate s into the s minus 2, So on the other side, you have to multiply by e to the at, e to the 2t. So I'm going to use this, the other translation theorem. Okay, that's it. So the Laplace inverse of f of s is going to be equal to the one that you have over here is going to be sine t. You see that would be the sine t. But since you translate s into the s2, so you have a coefficient e to the 2t. Give you the final answer. Okay, so as you can see, one from each. We check these numbers. Because otherwise, the rest are going to be checking when you do the differential equation. Okay, so you have your formulas. Okay, make sure you have these theorems available so that you compare them together. Otherwise, you may be confused. Okay, any question? So these are the type of the Laplace inverse that we're going to be interested in. Now, question number 3, I do it later on, Parvis. Okay, this is quite interesting. You see, look at this part D is the one. 0 to infinity sine t over t dt is pi half. This is a great problem in calculus. In calculus 2, it's improper integral. The only thing that you can do is you can use integration by parts and comparison theorem to prove that this integral exists. Just converge only. You can't do anything else. Okay, but when it's a converge, if you want to find it, you can't do it. You can't do it in calculus 1 or in calculus 2 or 3. You need to do it by using the so-called complex variables, complex functions. You change it to the complex form, something like e to the ix, etc., and eventually we find it. It's a great theorem. It's not easy to find. But the easiest way you can do it is Laplace transform. For the Laplace transform, I list these just for your information. List the A, B, C to give you the hint of how we're going to do it. You see, for this type of problem, there are 2 of these in calculus, or we call it first integral, even in physics. You see, look at this part C. The part C is the way I do it. You see, 1, 2, 3, 4. So you go through all this, you end up with the application of the 4. But the key is this one. Integral of 0 to infinity, f of t, t dt, is 0 to infinity, f of u du. That is the Laplace transform of the function. So if you compare them together, you see, compare them together. So this simply means this, what is this? This Laplace of f of t. So this means if you want to integrate 0 to infinity, f of t, t dt, integrate 0 to infinity, Laplace of f of t, which is on the top. So this means if you want to find the 0 to infinity sine, I just do this part. If I get time, then I come back and explain the other part. They're not difficult. Just you put them together to get the result. That you see for the part V, use this part. 0 to infinity, f of t, t dt is going to be 0 to infinity, Laplace of this function. You see, that's the one. Now you can bring any integral, improper integral that you cannot do it in calculus 2 here, and just do it. So one famous one is this one. 0 to infinity, sine t over t dt is simply 0 to infinity, Laplace of sine t. Okay, depends, we call it du, ds, it doesn't matter. So the Laplace of a sine is what? It's going to be 1 over, we say s squared, but since the variable inside the integral is u, it's going to be 1 over u squared plus 1 du. And you know this integral. Okay, it's improper, so we're going to limit up. Let's say t goes to positive infinity, integral from 0 to t. Okay, 1 over u squared plus 1 du. What's this integral? Give us a function whose derivative is 1 over u squared. 1 plus u squared. Tan
Inverse.
Tan inverse, very good. Tan inverse. It's going to be tan inverse of u, 0 to t. Okay, substitute, take the limit. So it's going to be limit of t goes to infinity. That would be tan inverse of t, for example, minus tan inverse of 0. When t goes to infinity, tan inverse is continuous function. So that gives you tan inverse of infinity. The tan inverse of infinity is pi half minus tan inverse of 0. You want a function, angle tangent is 0. That is 0. So that gives you pi half. So 0 to infinity. Sine t dt is equal to pi half. Great result. Search on internet, you will see the proof of the 0 to infinity sine t over t dt. If you want to do it in complex variable, I used to teach that course. I have a textbook on the complex variables. And so if you want to do it using that formula, we have something we call it contour integrals. Contour integral means we create a region, we integrate on that region. You already done calculus 3, you know that. Contour integral is a line integral. So we introduce a region, we integrate on that region, and eventually, when you take the limits, if you like, you end up with the 0 to infinity, sine t dt. Okay, that's a bit. But knowing that contour that you have to use is the key. Okay, for this one. There is another one, integral of e to the negative infinity. You know that normal distribution function. Again, this is, you can prove that it's a conversion only. But in calculus 3, we can do that one. In calculus 3, you have a nice example in your book that they give you this contour integral by the double integral, of course, you do it. But in complex variables, all of them can be done. It's not easy. Yes? No, this is a unique problem. So you've done it. I just wanted to show you the role of the Laplace transform. Okay, there are quite a bit. We can make one and give you one, but we have too many questions. Okay, but this is the one. So there is another one like the normal distribution type, the bigger. Okay, so that's the idea of number 3. So let's go to the so that was a Laplace transform. Now we need to solve some equations. Okay, we give 2 groups of the equation. Differential equation, ordinary one, differential equation with the unit step function. Ordinary one is number 4. We did a couple of them. Okay, over here. So what I do is I do number D. If I get time, otherwise I give you the solution of the others. I have to. The first one, probably we did it. The second one, we were difficulty, but we did this one too, okay? But I give you the solution of those because I want to make sure I get to the system of the equation. I do number 4 because 4 is higher degree. We haven't checked this one with the Laplace transform, of course, okay? So 4, that is, you want to solve the equation, okay? So use Laplace transform. Use the Laplace transform. Laplace transform to solve the equation. So that's a group 1. We give you 1. In this form, you don't need any translation theorem. It would be a straightforward. Algebra is more involved. You may have to do some partial fractions, okay? But otherwise, it should be done. So we do the part D, and I give you the solution for all of them. So this is it. You want to check to make sure that you remember that formula. Laplace of the derivatives, okay? Laplace to the y to the fourth degree or derivative minus 4y equal to the 0 with the initial condition y of 0 equal to 1, y prime of 0 equal to 0, y double prime of 0 equal to the negative 2, and y double prime of 0 equal to the 0. You know that. If you want to do it right away, you have to. Yes. What's that? One of them is triple. The last one is trigger. Okay, you need 4 conditions to be able to do it. You know that if you want to do it ordinary way, it's just characteristic equation r to the 4th minus 4 equal to 0, and then you do the job. But we want to use Laplace transform. Okay, take the Laplace of both sides. You know that how to do it. Solution. That's it. So I'm going to call, I like those notation that I use. My notation, if you like, okay? So suppose y equal to the f of t is the function, is the solution. Is the solution with the following condition. Condition is f of 0 is 1, f prime of 0 is 0, f double prime of 0 is -2, and the f tiers of 0 is 0. Okay, that's it. Now take the Laplace transform. So the Laplace of the 4th order of the derivative, f of t minus 4 Laplace of f of t equal to the 0, because Laplace of 0 is 0. Now change this one into the Laplace of f of t. Remember, that we write it down is 4. So the formula is s to the 4 Laplace of f of t. Then you reduce the power of the s, and you multiply by f of 0, f prime of 0, f double prime of 0, etc. So it's going to be minus s cubed f of 0 minus s squared f prime of 0 minus s cubed f double prime of 0. Okay. So this is it. And the last one is going to be simply the 3rd derivative. You lower the power of the s, start with the 4. Okay, 4, 3rd, 2nd, 1st, and the 0. Okay, that's one. But we have minus 4 Laplace of f of t equal to the 0. Apply the initial conditions and then simplify it. So what do we have? F of 0 is 1, f prime is 0, f double prime is a -2, and f tiers is 0. Okay, so what's going to be the leftover now? S to the 4th Laplace of f of t minus s cubed. This will be out. It's going to be plus 2s. Okay, this will be out. Minus 4 Laplace of f of t equal to the 0. Take out the Laplace of f of t and make sure you get the characteristic equation. So that gives you s4 minus 4. Okay, Laplace of f of t. And the leftover, you move them to the other side. So it's going to be s cubed minus 2s. Okay, which is not bad. Okay, now we find the Laplace of f of t. So the Laplace of f of t is going to be equal to, okay, it's going to be equal to the s cubed minus 2s over s squared minus 4. Sorry, s to the 4th minus 4. So you have to simplify it. You factor out the s on the top, so that gives s squared minus 2. And you write this one as s squared minus 2 times s squared plus 2. So that's happened to be easy. These two would cancel out. You get the s over s squared plus 2. And easily done. So f of t is going to be Laplace inverse of s over s squared plus 2. You know that you have the s on the top, so this is cosine. Okay, that's cosine of what? Root 2 of t, the final. Okay, So the purpose, if they give you higher degree or higher order, the purpose is how you apply these the formulas. But the other one takes more times, okay, and check the solution. If we didn't get time to do it. Okay, I give you a break if you like. Come back, we have to do differential equation with the function, unit step function, and of course, the system of the equation. So you have the 10 minutes and we continue.
I forgot to take that quiz back last Wednesday, or I mean, on Monday, because I wasn't here on
Okay, let's get the type 2. The type 2 equation would include some unit step function. Okay, so you will one of them, you have 3 over here, A, B, C. Okay, so let's try the first one to get the idea. So this is the type 2 differential equation that we are going to be questioned. So we need all these translation theorems that we talk about for this one. Okay, so that would be number 5. Again, use the Laplace transform to solve the equation. Laplace transform to solve the equation. Okay, part 1. Part 1, this is the function y double prime. This is the equation y double prime plus y equal to h of t, and then h of t would be introduced. Initial conditions are y of 0 equal to the 0, y prime of 0 is equal to 1, and the function h is defined as follows. H of t is equal to 1 when the t is between 0 and 3 pi, and it's equal to the 0 when t is greater than equal to the 3 pi. It would be a unit step function. So it's a unit step function at, okay, the base is c is 3 pi. The first thing to do for this type of problems, you better find the Laplace of this function first, because you are going to use it, okay? So the solution is going to be, look at the h function. You see the h function is not exactly the unit step function. Remember, it's a complement. The one that we have is 0, 1. In this case, it's a 1, 0. Remember the way we are going to write this one. So note that your h of t is going to be 1 minus u of 3 pi t. Okay, because they flipped 0 and 1 to get these numbers. So it's going to be 1, 0. This is, so you change it because 1 minus 1 would be this is going to be u3 pi t. You get the 0. It's a 0, 1. When you subtract it, you get the same one. Okay, so that make it easy for you to find the Laplace of h of t. Laplace of h of t would be the Laplace of 1, okay, which is 1 over s, minus the Laplace of the unit step function is going to be e to the, remember, negative 3 pi s divided by s. So that would be the Laplace transform of h of t. We have to find. Now we go back and we organize the problem, the equation, by taking the Laplace transform and see what would happen for this, okay? So there you are. I'm going to suppose y equal to the f of t is the solution. Okay, is the solution of the equation. The solution with the following condition, that f of 0 is equal to the 0 and f prime of 0 is equal to 1. So take the Laplace transform of the both sides of the equation. We're going to have the Laplace of f double prime of t, okay, plus the Laplace of f of t equal to the Laplace of h of t. Now for the f double prime, change it. It's going to be s squared, the Laplace of f of t, okay, minus s times f of 0, and then minus f prime of 0. That's the Laplace of the second derivative. And then it's a plus the Laplace of f of t equal to the Laplace of h of t, you already got it. Is 1 over s minus e to the negative 3 pi s over s. So apply your initial conditions. Initial conditions that you have is f of 0 is equal to the 0, and the f prime of 0 is 1. So this means this part will disappear. Okay, this would be 0, and f prime of 0 is 1. So we are going to arrive at, okay, going back here. So we get s squared Laplace of f of t. This would disappear, so that give you a minus 1. Minus 1 plus the Laplace of f of t. Okay, Laplace of f of t, and is equal to the 1s, 1 over s, e to the negative 3 pi s over s. Now take out the Laplace of f of t to get that characteristic equation to check. So that gives you s squared plus 1. Okay, Laplace of f of t. So you move the negative 1 to the other side. So you get 1 over s minus e to the negative 3 pi s over s at the plus 1. Okay, now divide by s squared plus 1. So Laplace of f of t is going to be equal to the 1 over s times s squared plus 1 minus e to the negative 3 pi s over s squared plus 1. Okay, and finally a plus 1 here. 1 over s squared plus 1. Yes. Okay, so f would be the Laplace inverse of those group. So f of t is going to be equal to the Laplace inverse of the first one, 1 over s squared plus 1. Okay, this would be the one that we're going to use translation. Laplace inverse of e to the negative 3 pi s, s times s squared plus 1. And the last one is easy. Laplace inverse of 1 over s squared plus 1. Okay, the last one is easy, it's the sign. For the second group, you know that for this one, you forget about e to the negative 3 pi s, because that gives you a unit step function, u3 pi t. Then you have to take care of the leftovers, which is 1 over s times s squared plus 1. If you find the Laplace inverse of the leftover, which is f of s, f of t, then you change it to the f of t, t minus c, and then you do that. And you have it also over here. It's always the same. Always going to be the case. Okay, yes.
So during an exam, we had a question like this, would we be able to just find the inverse Laplace of the first one and then we just assume? that
Of course, yes, that's a plan. That's a plan, yeah. That's plan, we know that. As soon as we find the first one, then this would be just f of t minus 3 pi. And the last one is clear. So the main thing is just a partial fraction for this, and then the leftover, and we're done. Okay, so we check this one. So let's do the partial fraction for this one, which is not difficult. Okay, so you have the s and you have the s squared plus 1. And on the top is a constant. Okay, it's a constant. So the way you are going to create the constant, you need to take care of the s squared. So if you put the 1 here and the negative s, you are done. You see, because that gives you s squared plus 1. S squared plus 1 minus s squared. So the s squared and s squared would cancel out, and you're done. Okay? Because of the constant here. You don't need to write, if you want to do it, it's going to be a1 over s, a2s plus a2. No. Just get these numbers right away. Okay? So that's it. So it's going to be 1 over s minus s over s squared plus 1. Since it's a constant, you can create it right away. you get these numbers. Okay, now we are ready to get the Laplace inverse. So what is going to be Laplace inverse of 1 over s times s squared plus 1? It's going to be Laplace inverse of 1s, okay, 1 over s,
1.
which is 1, minus the second one, cosine. Yes, cosine t. Cosine t. That's the one that you call f of t, if you like, and then automatically you get the second one and you just continue, get the result, okay? Since I already got f of t, I'm going to call this one g of t. Okay, as soon as you call this one g of t, you are ready to get the next one. Okay, so what's going to be the next one? Laplace inverse of e to the negative 3 pi s over s times s squared plus 1 is going to be, you have a unit a step function at the base 3 pi of the t times g of t minus 3 pi. Remember, t minus c. So as soon as you find the first one, you already got the second part too. You don't have to write, you can go up like and write it, It's going to be 1 minus cosine of the t minus 3 pi. Will that save you time? And the Laplace of the last one, we know it. Laplace inverse of 1 over s squared plus 1 is simply sine t. So in short, this is the final answer. F of t equal to the 1 minus cosine t, or just g of t, okay? So in short, is going to be g of t. Okay, g of t minus u 3 pi t, g of t minus 3 pi, plus the sine of t. If you write in this formula, you have to remind us that when or where g of t is simply what? 1 minus cosine t, and then do that. Otherwise, you can list it. You can give us full, full version of the function. Okay? So it's nice to write it down in this way. Otherwise it's going to be 1 minus cosine t minus upt. Okay, this is going to be 1 minus cosine of the t minus 3 pi. It's going to be the same thing. Okay, so make it short for yourself. Going through these numbers, and then we are done with this one. Okay, any question? So you are going to be involved with one of these. Okay, this partial fraction one, and eventually the unit step function give you the result. Okay. Again, I'll go with the system of the equation. If I get time, I'll come back to the other two. Otherwise, you will see the solution yourself to get these numbers. Okay. So part C is a little bit more involved. Takes a little bit more time to do it, but all of them can be easily done. So let's go to the next topics that we have. Then we come back if we get time. The next topic is going to be using Laplace transform to solve the system of the equation. Okay. And so we talk about it, the way we can do the system of the equation. There are going to be two functions. We take the Laplace transform. We change the system into the algebraic system. Your algebraic system would have two unknown, and those are going to be the Laplace of two functions. Okay, so it's not going to be difficult to handle. The other system that we're going to be interested in is the linear system that you can use the eigenvalues term to be able to do. Okay, so let's do number 6. Let's solve the system. Use the Laplace transform. So when we say you have to, you use the Laplace transform to do it. Laplace transform to solve the system. Okay, to solve the system. The system is this one. Try to give you something that can be done easily because it takes time. So the system is dx dt plus y equal to t. That's the first one. And the second one is dy dt. Dy dt plus, okay, plus 4x. 4x equal to 0. Remember, x and the y are function of t. X and the y are function of t, so you can have a t here. Okay, and the initial condition is that the x of 0 is equal to 1 and y of 0 is equal to 2. Can I say with this, or I change it into the f of t and g of t, so that would be easier to handle it. Okay, so the second method that we talk about it, for the time being, you cannot use this. You have to wait, because this is not homogeneous system. That's why we give you something which is going to be different. Okay, but eventually you are going to be able to do this one as well. So what I'm going to do, I change the notation. You know, this is optional. So I'm going to suppose, okay, I suppose that x equal to the f of t and y equal to the g of t are going to be solutions. Okay, solution. Okay, solutions of the system with initial condition that f of 0 is equal to 1 and g of 0 is equal to 2. I change them into this form, which is more familiar. So now the system of the equation will be changed into, it's going to be f prime of t plus g of t equal to t. This is the first equation. And the second equation is going to be g prime of t plus 4f of t equal to this. Okay, that would be the system in this notation. Now take the Laplace transform of all of them. Change it. It's like, you know, like the one that we did before, but we do it for 2 equations. Okay, take the Laplace of each equation, Laplace of f prime of t plus the Laplace of g of t is equal to the Laplace of t. And then the second one, Laplace of g prime of t plus 4 Laplace of f of t is equal to this. Change it again as we did it before. Laplace of the derivative. So you continue. For the first part, Laplace of f prime is going to be s Laplace of f of t minus f of 0. The second one as is, Laplace of g of t equal to Laplace of t, which is 1 over s squared. Okay, and is equal to 1. The second one, g prime, is going to be s Laplace of g of t, okay, minus g of 0 plus 4 Laplace of f of t equal to the 0. Apply the initial conditions. So you have f of 0 equal to 1, g of 0 equal to 2. Okay, f of 0 equal to 1, so this would be 1. G of 0, 2, so that gives you 2. So this is it. So S Laplace of f of t minus 1 plus the Laplace of g of t equal to the 1 over s squared. Second one, S Laplace of g of t minus 2 plus 4 Laplace of f of t equal to the 0. Okay, that's all you have. going to move 1 and -2. I can do it now or I can do it later. To the other side. To make it algebraic system. Okay, Laplace of f of t plus the Laplace of g of t is equal to the 1 over s squared plus 1. That's the first one. And for the second one, s Laplace of g of t plus 4 Laplace of g of t is equal to 2. You see now it's an easy system. And we can solve it. Okay, so that's a 4 Laplace of f. Okay, you know, you can eliminate one of them and then you continue to get these numbers. Okay. You know, if I write this one, you know, it doesn't matter. So both of them are going to be the same if you want to eliminate it. So if you want to, G would be easier. If you want to eliminate the G, so we need to multiply the first one by -s. If you want to have -s, then the G will disappear, then we'll be able to do the job. Okay, so multiply the first one by a -s. So -s squared, Laplace of f of t, okay, minus s, Laplace of g of t is equal to it's going to be -s over s squared, and the minus s. Okay, so the second one, I write down in this form, Laplace of f of t. Okay, so plus s, Laplace of g of t. Laplace of g of t equal to 2. So add them together. So the g will disappear. And over here is a -s over s squared. So this would be -1 over s. Okay. And this is also s. So what's going to be the leftover? The leftover, we get -s squared Laplace of f of t and the 4. So if you add them together, it would be something like 4 minus s squared Laplace of f of t. And on the other side, we get -1 over s minus s and the plus 2. Okay, now we can find the Laplace of f of t. So it's going to be Laplace of f of t is going to be equal to, you divide. So this is going to be -1 over s times 4 minus s squared. Okay, so this is going to be one of them. And then minus s over 4 minus s squared. And eventually it's going to be 2 over 4 minus s squared. Okay, so that should give you Laplace of f of t. And then we can continue to get the result. Okay, I'm just checking the one that I think I have. Okay, so you have to do the partial fractions. Okay, to do it, check to see if I have the result of that part. So I can show you. So this is where we end up. We get 4 minus s squared. Yeah, it's all right so far. So I got some of the numbers so I can use it. Okay, there you are. This is s over 4 minus s squared. If you like, you can apply this negative sign bottom here, make it to the s squared minus 4. And this would be s squared minus 4. And you can, you have to break that. Okay, you have to use the partial fraction to do it. I can do it as is, it doesn't matter. Okay, so I go to the next page. And I have to break these two. It's easy to break because of the constant on the top. Okay, I can take care of this one. I can break it, or I can use the, remember, s squared minus 4. I can use the cosine hyperbolic function to do it. That would be easier. And that will take us to the last part. Okay, so there you are. So I have to rewrite this one to get it done. Okay, so what I have is Laplace of f of t is equal to, I applied also a negative sign to make it easier. So the first one is 1 over s times s squared minus 4. Okay, that's the first one. The second one is going to be plus s over s squared minus 4. Okay, and the next one that I have, I change it to the negative, so it's going to be 2 over s squared minus 4. Okay, in fact, we can simplify the last two. This is s squared minus 4, and s squared minus 4. It's going to be s minus 2. You can simplify this. That's it. So it's equal to the 1 over s times s squared minus 4. This is going to be plus. You have the s squared minus 4. The top that give you s minus 2. So you factor the denominator, s minus 2 times s plus 2. So we get 1 over s times s squared minus 4, and the plus 1 over s plus 2. Can be, easily done. So I have to break the middle one to be able to continue, and I break it easily. I can factor s squared minus 4, but I'm going to use the hyperbolic function. So I have s as a denominator, s squared minus 4. I don't like the s. So there's a constant on the top, so it's going to be s. And this is going to be 1. So let's see if you have to change it. If you find the common denominator, the top would be s squared minus 4 minus s squared. So the leftover would be negative 4. So I need to change it to the negative 4. So this would be negative quarter. And this is going to be negative quarter. And the plus 1 over s plus 2. Yes, what's question? Question?
Wouldn't you have a minus sign in instead of a plus sign if you?
This is going to be no, eventually, it would be embedded in that. Okay, so there you are. So I repeated, this is a negative quarter over s plus that is a negative quarter times s over s squared minus 4, and this would be 1 over s plus 2. Now we are ready to find the Laplace inverse of this one. Okay, so if you just multiply them together, then the s would be disappear. Yes, one of them must be this. The first one is going to be that give you negative, and that give you 4. Yes, that would be right. Because we get it. Okay, again. Now we find the ft. F of t is going to be equal to Laplace inverse of this. Okay, are you ready? The Laplace inverse of the first one. It's going to be a quarter. And that's it. You know that the 1 over s is the Laplace inverse of 1. So this is the first one, quarter. Second one, I pull out the negative quarter. You know that s over s squared plus 4 is cosine of the 2t. It's a negative, so it's going to be cosine hyperbolic of the 2t. That's the one. And the last one is simply e to the negative 2t, e to the negative 2t to get the final answer. Okay, so that is it. Okay, I didn't make any mistakes. This is s at the 2 minus s that was a negative 1 over s plus 2 minus s. I divide the both sides by 4 minus s squared. So this is what I got over here. Okay, that was a 2. Yeah. I mean, now, the way I did it, I just didn't simplify the other one. So I got something like sine hyper of the 2t. But when you put in, that's correct. Yes.
Please, having gone first.
Yeah, of course. Yeah, otherwise, you have to break it again. Yes.
And we can leave it like that. We don't have to.
Yeah. That's it. Yeah. Of course, you know that you're not done. Because that's f of t. Yeah, we don't simplify it. That is going to be the final answer. The only thing that we do, if there's going to be any like terms, we combine them together. Otherwise, it's not. Yes. If you change it, yeah.
Do we use the hyperbolic sign?
Of course, yes. Yeah, we talked about it before. 1 over, you see, if you get the a over s squared minus, if you get a over s squared minus 4, that would be sine. So why not? We can use it. Okay. So we are not done. That's f of t. So we have to go back and substitute to get the g of t. So let's see what we have. You go back to one of these equations that you have. You get the g of t. Remember? So what I'm going to do is this is it. The equation that we have, maybe this is an easy one because the Laplace of g of t is already here, and then we can do the job right away. Okay, so go back to one of those equations to get the. So I take it from the equation number 2. So the equation number 2 is this one. S is going to be S Laplace of f of t. Okay, plus Laplace of g of t. Laplace of g of t, and on the other side, you have 1 over s squared plus 1. 1 over s squared plus 1. Okay, and there you are. You are going to substitute to get these numbers. And there is an s here. If it was a number, that would be easier to handle it. But no, we can't do it. We have to do it. Okay, and so there you are. Find the Laplace of g of t. Laplace of g of t is going to be 1 over s squared plus 1 minus s times the Laplace of f of t. Okay, you already got the Laplace of f of t, substitute, and then try to simplify it. So what's going to be the result? It's a Laplace of g of t equal to, remember this is the Laplace of f of t. That's the Laplace of f of t, and we are going to multiply by s to get these. Okay, it's a 1 over s squared plus 1 minus s times what? 1 over s squared plus 4 plus s over s squared minus 4 minus, okay. Sorry, I simplified a little bit. Okay, the one that we simplified was, that's s over s squared minus 4. You see the simplest form is this one that we did. So it's going to be 1 over s squared minus 4 and plus 1 over, okay, plus 1 over s plus 2, because we simplified. We simplified to get, okay, to get this part. Now multiply by s and take the Laplace inverse. So it's going to be Laplace of g of t is 1 over s squared. If you multiply the s inside, so that you 1 over s squared minus 4. And the last part would be is a minus. And the last part would be minus s over s plus 2. Okay. So we are ready to get the g of t. Okay, for g of t, it's going to be Laplace inverse. It's the Laplace inverse of 1 over s squared minus the Laplace inverse of 1 over s squared minus 4. Okay, and minus Laplace inverse of s over s plus 2. To get the g plus, okay, it's going to be plus 1. Laplace inverse of 1. Okay, so it's not difficult. All of them are almost available. Okay, 1 over s squared, that's 1 over s squared. T. Next one. Okay, it's going to be sine hyper, but you need the 2 on the top. So it's going to be negative 1/2 sine hyperbolic of, okay, of t. 2t, yes, 2t. For the next one, you have to do something about it. It's s over s plus 2. You can divide it or add subtract. So it's going to be minus Laplace inverse of 1 minus what? Minus 2 over s plus 2. And the last one, Laplace of 1. Okay, it's just 1 over s. Sorry?
The inverse of 1?
Laplace inverse of 1, sorry. Which is going to be what? This because the 1 is s to the, maybe we, what is the Laplace inverse of 1? Laplace inverse of, maybe we simplified first. Okay, we can put them together over here. Okay, find the common denominator. That would be better to be able to take care of it. Okay, because this is all you get. Okay, so I didn't miss anything over there. Okay.
The ones with cancel out, right? From the inverse. The cross of 1 minus 2 over s plus 2. That those ones with cancel out.
Oh, that's it. Yeah, that's right. Yeah, it's the same as if we find the common denominator first, and then we go for it. Yes, you are right. Okay, so this is going to be simply what? It's a Laplace inverse of 1. So we get the t minus 1/2 of the sine hyper of 2t. So this part simply would be plus, okay, plus 2 e to the negative 2t. That give you the final answer. Okay, so you can, I didn't see the one, otherwise I put it together. Okay, so as you can see, it takes time. We try to give you something short, but this is a kind of shortest one that you can have. But we have to try. Okay, it's not bad to be able, to get it in case in future you see it. You see when you do these type of problems in research, then you may solve one of them and publish a paper how you did find the solution of that system of the equation. So this is going to be the case now. So I'm going to I need to give you that linear one. I put a second order here, second order, just for your information. I give you the solution that you can see. You see the second order. The second order one, you get x double prime, y double prime. So it's not difficult, but when you substitute, you know that you have to substitute for the Laplace of the second derivative. Algebra involved is going to be quite a lot. But I just post the solution for you. You can get it. You know, when you simplify it, in fact, this one at the end is going to be so easy. But this is just a coincidence. It takes time. But there are a couple of phenomena in physics, if you read your book, that the result is going to be a system of differential equation of a second order. So you should have the experience that in case you have to do these type of problems, you have an idea, okay, to be able to do it. Yes.
Do you know one of those phenomena off the top of your head?
No, but I can bring it back for you. You see, I think it's something about the spring law or something, but it's in the book. So we usually, when we teach this system of the equation of second order, we start with that example, and we just go for it. But I can check it and tell you now. The original one that I posted for the previous years, we did have 3 problems with the second order because of the need of those type of problems. But it takes time. I can talk about it later for you when we get back to the system. Okay, so number 7 would be true match, but we may, we do it when we get to final review. That would take us to the last one. That algebraic solution using those eigenvalues, easy case. We have 3 cases. We give you 3 questions on the final, but for the time being, just only 1. Okay, number 8. Number 8, solving by the algebraic system. Okay, there you are. That would be your easiest question. Solve the system. This is the system. Intentionally, we write it down in matrix form to give you the idea that you have to use the matrix idea to solve this equation. So, okay, that's it. And the initial condition is given to you. X of 0 is 3, 2. So this simply means X of 0 is equal to the 3, if you like, and the Y of 0 is equal to 2. So you have the initial condition, means you have to find the C1 and the C2 first. Okay, remember the way we are going to arrange it, solution. And of course, there is an X here. Remember, X was X, the vector X and the Y, X prime is X prime and Y prime, but it's a matrix form, so you change it to the matrix form. What is going to be the matrix form? You are going to get a matrix of the coefficient, we usually call it A, 1, -4, 4, -7. Okay, if this is going to be the case, and you are going to have X prime equal to the A times X. Now you change it to the matrix form, and you can bring the solution that we already talked about it. Okay, remember the solution that we have. You have to find the characteristic equation that are A minus A, lambda I. You literally equal to 0 to find the lambda. And A minus lambda A minus lambda I. Remember, in the main diagonal, if you like, you subtract the lambda. So this is going to be 1 minus lambda, -4, and it's going to be 4, -7 minus lambda. You need this equation. Then when you want to use the vectors. So get the determinant of this matrix. The det of A minus lambda I is equal to multiply, cross multiply 1 minus lambda, -7 minus lambda, minus 4 times -4. So use the FOIL method. So it's going to be -7 minus lambda. Multiply the lambda inside. Again, it's going to be plus 7 lambda, and the plus lambda squared. And this would be a positive 16. Combine the like term, write it down in the quadratic form, lambda squared. That give you 6 lambda, and that would be that would be 9, which is very bad. Okay, I have to change it because it's got to be repeated solution. So we can't do it for the time being. Okay, I don't know why they made a mistake. I give you this one. Okay, let's continue to find the lambda. But this is not be intended for this quiz because we can't do it. Okay, and so in this case, you let it equal to the 0, so lambda 1 equal to the lambda 2 equal to the negative 3. I did check the solution, but I don't know why I give you this one. So I have a list of these. I have to try another one. Okay, this is the list that I'm going to put some of them as your take-home one to be able to do it. Okay, as practice. But sorry about that. I have to check. So let's try another one because we can't do this one. So randomly, let's check one of these to see if it's going to be the case. Okay, we're checking the first one. 1, 2, 4, 3. Okay, so I change it into, let's call it number 8. This is the equation. 1, 2, 4, 3, x. Somebody check to see if these eigenvalues are going to be distinct. So the solution is going to be x prime equal to the ax. So the a is this one, 1, 2, 4, 3. So what's going to be a minus lambda I? It's going to be 1 minus lambda, 2, 4, 3 minus lambda. Get the determinant of this one. That of a is equal to 1 minus lambda times 3 minus lambda minus 8. So that gives us a 3 minus lambda minus 3 lambda plus lambda squared minus 8.
Lambda is 5.
Sorry?
Should be -5. So like the solution.
You get a solution? Let me just check this one. So that give you, yeah, that's a distinct root, okay. So it's going to be lambda minus 5 times lambda plus 1. Okay, you let it equal to 0. So we have distinct root, okay. So we get a lambda 1 equal to the 5 and lambda 2 equal to the -5. Okay, so for the time being, we can do this one. Repeated one takes more time to do it. You will see it after the test. Okay, now we have to find the corresponding vectors, and then that will give us the general solution. Okay, so going back and find the vectors. So for lambda 1 equal to the 5. Okay, that's it. Lambda 1 equal to the 5. You go to that equation that we did have. The vector is going to be a minus lambda I times k equal to the 0, where your k is going to be k1 and k2. So you go to this format that we did over here and replace the lambda by, okay, lambda by 5. Okay, that's a quick way to find it. 1 minus 5. Okay, so it's going to be 1 minus 5. Okay, 1 minus 5 and 2. And the other part is 4, 3 minus 5. And this is going to be times k1, k2 equal to the 0. So if we simplify it, that would give us a -4, 2, 4, -2. times the K1 and K2, we need just one row, if you like, 0, 0. So if you multiply it, is a negative 4K1 plus 2K2 equal to the 0. And the next one is going to be the same thing. Okay, we just use one of the equation. It doesn't matter which one. So it's a negative 4K1 equal to the negative 2K2. We divide by negative 2 if you like. So K2 would be 2K1. It's a relationship between these two. You can use any number you like. So for example, use the K equal to the 1, and then K2, K equal to 1, the K2 will be equal to 2. So the corresponding vector is 1 and 2. It's not the unit vector, you know that. You can have many, many, many. So that would be the first part. That gives you one solution. You can call it X1. So the X1 is going to be 1, 2, e to the, okay, e to the 5t. That is the first one. You have to repeat it again for the second one. Lambda 2. Lambda 2 is negative 1. So go to the same system that we did it. So it's going to be 1 minus negative 1. 2, the same version. It's going to be 3 minus negative 1 times the K1, K2 equal to the 0. So this time that gives you 2, 2, and this would be 4, 4. Okay? And that's a K1, K2 equal to the 0, 0. The first row give you 2K1 plus 2K2. You don't need the second one really. The first one will do it for us. So from the first one, you get 2K1 equal to the negative 2K2. You simplify it. K1 equal to the negative K2. You can pick any number you like. K1 equal to 1. K2 equal to the negative 1. So the second solution, X2, is going to be this vector, 1, negative 1, e to the negative t. So that's the first and the second one. Your general solution, X equal to the C1, X1 plus C2, X2. Okay? So this is going to be equal to the C1 times X1, 1, 2, e to the 5t, plus C2, okay, C2, 1, negative 1, e to the negative 2. Okay, so that will be your X. You can pick the components, okay, for the X and the Y. So if you pick the first component, X is equal to the what? It's going to be C1 e to the 5t. You see C1 e to the 5t plus C2 e to the negative t. The second is going to be 2C1 e to the 5t minus C2 e to the negative t. These are going to be the final answer. Yes. No, that when you pick anything else, these constant are going to be just constant. It depends on the initial condition that you have. You see, because the system that you solve is a dependent system. So you have many, many solutions. But in order to write your general solution, you need one of them. Because when you add the constant, you create what? All the solutions. So it doesn't matter.
Starting the eigenvectors on their own, they solve K1 and K2, or taking K2 and K1 and solving these vectors, do they get different valid answers for those eigenvectors? Because there are more than one.
Yes, there are more than one, infinitely many. So the way, in fact, they do it in linear algebra, you know that. Instead of, when you have, instead of 1, 2, we pick the K2 to be T. You know, if it's going to be T, then the K1 would be negative T. So you have t negative t. You factor out the t, it's going to be t times 1 negative 1. You know, we call it, you know, subspace spanned by these vectors. But since, you know, you go with this concept at the end, it's going to be the same thing. Okay. So we give you only with a distinct solution because we can't do the other one. Okay, that's it. So I post a take-home one for you. It's going to be extra 3, if you like. And that would be useful. Which is going to be the topics that's going to be covered on the test. So you focus on that. That's it. Okay. Have a good one. Bye. We finish this one.